In this video, we're going to be talking about numbers, specifically the difference between exact numbers and measured numbers, and then how to round measured numbers using significant figures. So the question we're answering is, how can you determine what to round to? So an exact number is either a counted number or a definition, and we do not round exact numbers. So if you count 6 balloons in the image, you keep it as 6 balloons. You never would round that to 10 balloons. You would always keep your counted numbers unrounded. And then a definition, for example, 1 foot is equal to 12 inches. We don't round those numbers. Definitions are exact numbers. On the other hand, measured numbers are rounded. Whenever we're making a measurement, we're gonna be estimating something, even if it's a really, really good estimation. There's still some sort of estimation happening. You must have one uncertainty value whenever you measure something. So for example, here's our paperclip. Notice that it is somewhere in between. So this is in centimeters. Each of these little tick marks is 1/10 of a centimeter. So I have 4.1, 4.2, and so on. And it is somewhere in between 4.8 and 4.9 centimeters. So instead of writing 4.8 centimeters or 4.9 centimeters, I'm going to have some sort of uncertainty digit. So in this case, I'm going to say it's 4.84 centimeters. So that last 4 is an uncertainty digit. Somebody else might say, I think it's 4.83 centimeters, and we would be equally right. We're making some sort of estimation. So we're going to round our measured numbers to one uncertainty value. So here's a graduated cylinder. If I am measuring a liquid in there, the liquid will have this thing called a meniscus. A meniscus is this U shape, and that just happens when you put a liquid into a graduated cylinder. Because the liquid sticks a little bit to the sides of the graduated cylinder. And so you measure from the bottom of the meniscus. So notice that this graduated cylinder, each of these large lines represents 10, but these little tick marks is 1. So I have 20, 21, 22, and so on, 30, 31, 32. So I can see that the bottom of my meniscus is very close to 31, but it's a little bit higher. So it's somewhere in between 31 and 32. So I'm going to say that it's 31.1 milliliters. Now, if it rested exactly on this line, it was really pretty exact, then I would measure this as 31.0 milliliters. So I still need that uncertainty digit. That 0.0 tells whoever's reading my number that it rested on that 31 line. It wasn't a little bit higher or a little bit lower. So we can apply this to just calculate the density of a metal. In order to find the density of a metal, D equals mass over volume. So I would put this on scale, and I would put it in order to find the mass, and then I would put it in a graduated cylinder in order to find the volume. So I put it on the scale, and the mass was 11.3 grams. Because this is digital, it would give you an exact number. We can't really round that to anything. Whatever number is on the scale is the number that we would record. But when we measure the volume, we will need to have an uncertainty digit. So in this case, I put water in the graduated cylinder, and I filled the water up all the way to the 20 mark. So this was 20.0 milliliters. And then I put the rock in there, and the liquid, the water, went up to this point. So that's somewhere in between 24 and 25 milliliters. So I'm going to estimate that as 24.5 milliliters. So again, I have my uncertainty digit. So the graduated cylinder goes to the ones place. My measurement has to go to the tenths place. I need one additional digit. And then I find the difference. And so my volume is 4.5 milliliters. So when we start doing calculations, you'll need to figure out what to round your answer to. And so when you have measurements. And so the question is, how many digits should you round to, and how precise is your number? And so there are a few rules you need to know. The first rule is that non-zero numbers are always significant. So you can see in example 1, I have 1,245 meters. That would mean I have 4 numbers that are non-zero. So I have 4 significant figures. And so that means that each of those numbers lends to the precision of my measurement. In the second example, I have 3.57942 nanometers. So I have 6 non-zero numbers. So I have 6 significant digits. So now let's talk about zeros. If you have a leading zero, a zero that comes before the non-zero number, such as all of these zeros, they are never significant. So we do not include them in our when we talk about significant figures and the precision of a number, we don't include them. So this would just have 2 significant figures. So 0.000051 grams has 2 significant figures, the 5 and the 1. In my second example, you'll never ever write a number like this, right? 345.2, you never put zeros in front. But I just wanted to show you that these are leading zeros as well. And this would only have 4 significant figures. Only the non-zero numbers count as significant. Captive zeros are always significant. So whenever there's a zero in between 2 non-zero numbers, it will be a significant digit. So 3.02003 times 10 to the 14th grams has 6 significant figures. All of these digits are significant. There's no leading zeros, and all of the zeros are captive. And then the non-zero numbers are always significant. And same with here, 402 liters, that zero is captive. So all 3 of these digits are significant. So I would have 3 significant figures. Ending zeros are a little bit trickier. So they're only significant if there's a decimal point. So sometimes they're significant and sometimes they're not significant. So just a reminder, leading zeros are never significant. Captive zeros are always significant, and ending zeros are significant if there's a decimal point. So in this case, I have these 2 leading zeros, so those are not significant. I have a decimal point, and I have an ending zero. So this would be 2 significant figures. 0.030 moles has 2 significant figures, that 3 and the 0. In my second example, I have all of these ending zeros, 4 ending zeros, and no decimal point. So in this case, I only have 1 significant figure. Only the 1 here is significant. This tells me that I measured something at 10,000 grams on a very imprecise scale, right? I couldn't even round to the thousands place. I only knew to the 10,000s place. In example 2 and example 3, this number looks very, very similar, and you might say it's the same number. It is not the same number in science and when we're taking a measurement. So in example 2, we have 420 centimeters with no decimal, which means that this just has 2 significant figures. That ending 0 does not count as significant because there's no decimal. So what does this mean? This means I have a ruler. I'm measuring in centimeters, and my ruler, this is just a portion of my ruler. It has 300 centimeters marked, it has 400 centimeters marked, and it has 500 centimeters marked. And when I measured something, it came up to somewhere here. Okay, so I'm measuring this big long thing, and it comes up to this point right here. And so somebody looking at this might say, okay, that looks like 430. And somebody else might say that I think that's 420 centimeters. And so notice this 2 right here is an uncertainty digit. It's an estimated value. In my fourth example, 420 with a decimal point, so this ending 0 is significant. So this has 3 significant figures. So what does this mean? This means that the tool that I used was much more precise. So again, I have 300, 400, 500, and my X landed on the 420 mark. So I have these tick marks in between that tell me 410, 20, 30, 40, 50, 60, 70, 80. Oh, I'm missing one. There should be 90. Sorry about that. And then 500. So you should be 10 tick marks in between both of these numbers. I apologize. So this number here tells me that my 0 is the uncertainty digit now. I know that it's 420 something, and I'm estimating that it's exactly on the line. And so this is a much more precise measurement than an example 3. In example 3, right, it could have been a little bit off the line or a little bit behind it, and I could still estimate that as 420.